Chapter 23, Computational Chemistry, Section 23.2, Molecular Mechanics. The most efficient method to construct a potential energy surface of a molecule is via molecular mechanics calculations, in which empirical equations are used to calculate the potential energy of the given molecular structure relative to its equilibrium structure. The equilibrium structure of the molecule and the empirical parameters used in the equations come from experimental measurements or accurate quantum mechanical calculations. The simplest empirical equation that describes the potential energy of a diatomic molecule is this: 1/2 times the force constant K times x squared, where x is r minus re, the actual bond distance minus the equilibrium bond distance. The force constant K and the equilibrium bond length R sub E come from experimental data or accurate quantum mechanical calculations. A more realistic model should include the third and even fourth power of x to introduce the inharmonicity of the vibration of the molecule. So this is for harmonic oscillators. For a real molecule, we can either include higher order of x or we can use Morse potential. The simplest empirical equation that describes the potential energy of a triatomic molecule, such as water, is this: we have 1/2 k x1 squared, 1/2 k x2 squared, and 1/2 k sub theta minus theta equilibrium squared. So here K is the force constant. For water, we're assuming the force constants for both OH bonds are the same, K. X1 is the displacement of the first OH bond, X2 is the displacement of the second OH bond. And over here, the equilibrium bond angle is roughly 105 degrees for water. The theta is the actual bond angle. And somehow we can obtain the value of K sub theta and this K either from experiments or from high-level quantum mechanical calculations. Again, X denotes the displacement of the bond distance, which is the actual bond distance minus the equilibrium bond distance. Theta sub EQ is the equilibrium bond angle. And this equation is used to describe harmonic oscillations, both bond stretching and bond angle changing or bending motion. A more realistic model should include inharmonic corrections and also the coupling between the change in bond distance and the change in bond angles. The downside of the molecular mechanical calculations are: 1, we cannot compute the electronic structure. So all those variables are the positions of the atoms. 2, the empirical parameters are needed to do molecular mechanical calculations. And those empirical parameters come from experiments or high-level ab initio or quantum mechanical calculations. And 3, molecular mechanical methods are often inaccurate. For example, if you want to describe the resonance energy of a conjugated molecule, it can be hard to do.